Okay, let's talk a little bit about weak acid, strong base titration curves. So this is a little different than the strong acid, strong base case we did previously. In this case, we'll still consider 0.1 molar acid, 0.1 molar base, except in this case, we're going to change the acid out to a weak acid, acetic acid. So we'll have 100 milliliters of 0.1 molar acetic acid reacting with potassium hydroxide to form water and potassium acetate. So again, both solutions are 0.1 molar, but I'll start with 100 milliliters of the acetic acid, and we're going to add potassium hydroxide to that. So what we're going to look at first is calculate the pH before adding base. That'll be similar to equilibrium calculations we've done in the past. Then we'll look at it somewhere in the middle, 20 milliliters of KOH added, again, like the previous example. And then we'll look at it at the equivalence point or after we've added 100 milliliters of KOH. So looking at our problem, so let's just consider the 0.1 molar acetic acid at first. So that's part A. And so we're going to have, it's just going to be an equilibrium problem like we've done already. So it's going to be an equilibrium with H plus CH3 COO minus. So Ka was equal to the concentration of H plus, concentration of the acetate over the concentration of the non-ionized acid. This should look pretty familiar by now. We're going to assume these concentrations are X and that this one's roughly unchanged. So that reduces to X squared over 0.100 equals our Ka for acetic acid, which we've been using, is 1.8 times 10 to the negative fifth. So then X squared equals 1.8 times 10 to the negative sixth. And then we're going to take the square root of that. So square root of 1.8 times 10 to the negative sixth, which will give us 0.0013, we'll say, molar concentrations. That is equal to our H plus. Now, so the pH then at that point is going to be negative log of 0.0013. I'm holding a few more decimal places in my calculator. And we get a pH of, say, 2.9. So that'd be the pH before I did anything. So that's higher than the strong acid, strong base case. 0.1 molar strong acid to have a pH of 1. So that's a bigger pH than the pH of 1, which was the strong acid case. And so we find that the pH is higher because the weak acid is less ionized than the strong acid. Now part B is going to be a little bit more complicated because as I generate product in terms of the salt, I'm going to build in a concentration of my conjugate base to this weak acid. So somewhere in the middle, I'm likely to be in a situation where I've got a buffer. So looking at that, if I add 20 milliliters, how many moles are we going to have? So our moles of acetic acid that I have in excess is going to be 0.100 moles per liter times 0.100 liters minus 0.100 moles per liter times 0.02000 liters. So our moles then are going to equal the difference. And that'll give us 0.0080 moles of acetic acid in excess left. Now, if I look, this is the amount of sodium hydroxide I added in moles. It is also the number of moles of our potassium acetate that is produced. And so the product of those two is 0.0020 moles. This is equal to KOH added, but it's also equal to the amount of moles of my acetate ion that is formed, which is the important part, because whatever of this is consumed is going to, if I consume this, I form this in equal proportions, right? All the coefficients are 1, so there's no more complex stoichiometry. So if this gets used up, this gets formed. So the amount of hydroxide I added is the amount of this formed, and so that's my moles of my conjugate base formed after the addition. So then, if you remember, our Ka was 1.8 times 10 to the negative fifth. Our pKa for this acid, as we've used it several times before, is 4.74. And that's just the negative log of this. So our pH is equal to pKa plus the log of the concentration of the salt divided by the concentration of the acid. So 4.74 plus the log of our salt, 0.002 divided by 0.008. And so in this range, we're forming a buffer, therefore using the Henderson-Hasselbalch equation. And so we run that through our calculator. And so our pH at this point, keeping our sig figs consistent with that, we'll call it 4.1. Now, that at that point's a buffer. Now, if we consider the last point, C, and we're going to consider it after we added the full amount of 100 milliliters, which means all of the acetic acid's been neutralized. So if we add 100 milliliters of this, it's going to use all this up, and what I'm going to have left is a solution of potassium acetate. Potassium is a spectator ion, it's neutral. What I'm really concerned about is the acetate ion. So we got CH3COO minus plus water, equilibrium, acetic acid, and hydroxide. And it'll work pretty much the same as our first case. with a little bit more effort because now I've got a base instead of the weak acid. But we need to think about what concentration is this at the equivalence point. So if I had 100 milliliters of this, 100 milliliters of that, I've doubled my volume, so my concentration of acetate initially is 0.0500. And we're going to need our Kb. So our Kb is going to equal 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. And we're going to have to run that through our calculators to get the Kb for the conjugate base. And so we get 5.6 times 10 to the negative 10th. Now we can work it pretty much like the problem up here. So our Kb is equal to concentration of our acetic acid, concentration of hydroxide over the concentration of our acetate ion. So that's going to essentially end up being x squared, but now divide by 0.050. And that'll equal 5.6 times 10 to the negative 10th. So x squared is, and I'm holding these again in my calculator, even though I'm rounding off on paper. And so we're going to square root that answer. And so we'll get 5.3 times 10 to the negative 6th. Now, if we look, that is equal to the concentration of our hydroxide ion. Not hydronium, but hydroxide ion. So if the POH is equal to negative log of 5.3 times 10 to the negative 6th. So negative log that answer. We're going to get a POH of 5.3. But the pH will be 14 minus 5.3. So we'll subtract there. And we get a pH at the equivalence point of 8.7. Notice that's a bit above the neutral pH of 7. If you think about it, the acid is weak, but the base is strong. If we look back at our initial reaction, that's a weak acid, that's a strong base. So think of it like a tug of war. If I got a strong base and a weak acid, I'm going to end up on the basic side at the equivalence point. And so you got a strong base plus a weak acid. What that's going to lead to is a basic pH at the equivalence point. If we switched it and we had a strong acid and a weak base, we'd end up with a little bit of an acidic pH at the equivalence point, where strong acid, strong base is neutral. So if we look at it, here's a titration curve. It has a few features that are a little bit different than the strong acid, strong base case. One, you notice the pH starts a little bit higher, then it rises, but then it buffers out in this middle section because you form a buffer which causes the pH not to change quite so much. But then you still get a steep increase in the middle where the equivalence point's about halfway up this inclined portion. But notice it falls to the basic range, which weak acid with a strong base works very well with phenolphthalein because you're very close to the end point. And then it would flatten on out as you continue to go. Now, just like we were saying, if we did a strong acid with a weak base, they're going to look the same, but they're inverted, and the equivalence point is less than 7. The equivalence point is less than 7. And you just have to keep that in mind. Now, it gets really complicated. We're not going to focus on the weak acid, weak base titration curves. They get more complicated, and the endpoints and the equivalence points aren't going to be so clear even with the curve because you got multiple equilibria going on. And so we won't focus on that one for the purposes of this course. But they can be acidic or basic endpoints depending on which weak acid and weak base you're talking about.